let's start. So much. So I should apologize. Like last time, I think the ending was not ideal, right? In particular, I said that we proved the theorem, but then Yan Pen kindly remarked that actually we didn't. So maybe we should finish the proof that we started last time. So let me recall what this theorem was. So we were discussing for the first time the real life example, well, almost real life. So H is L2 of R3, and A is minus Laplacian plus the multiplication operator by some function, where this function was the sum of two terms. So one of these terms is square integrable on R3, and the other one is bounded on R3. And then there are two conclusions. So one, so this depends now on the domain of definition. So A is self-adjoint on the domain of the Laplacian. And A is bounded from below. Maybe I just briefly recall what it is. So this means that there is a constant such that the quadratic form is bounded from below by the norm square times that constant. Actually, I will not be doing this part, and so you will do in the next problem set. You will do some small upgrade of Kato-Rehlich, and this upgrade will imply the boundedness from below statement. Now, but we actually haven't finished last time the proof of the first statement. So let me continue the proof. So we've shown last time that for good functions u, there is the following estimate. So it was something like this. So it's estimated in terms of the L2 norm of the Laplacian. Maybe I should better write the indices of the norms just to remember what they are. Plus some other power of the L2 norm of u. And there is such an estimate for all positive lambda. So in fact, so there is a family of estimates, and they are valid for all positive lambdas. Of course, one of the coefficients decreases if you increase lambda, another one increases. So there is a kind of trade. You can choose what you want. So now let's do the following. So let's look at the estimates for the action of multiplication operators. Let's say The easier one is V2. So let's estimate the L2 norm of V2 acting on U. So that's just an integral over R, V2 of x squared times the absolute value of x squared dx. And V2 is bounded, so we can estimate it. So here probably I should put 1/2. So this is estimated by the bound on V2. So the bound on V2 is its infinity norm. It's called its infinity norm, right? So times, and what remains in the integral is simply the absolute value of u of x squared dx. And that's the 2 norm of u. So if one of the functions small or equal, yeah, right. So if one of the functions is bounded and the other one is L2, then the L2 norm of the product is estimated as an infinity norm times the 2 norm. Now, what about this thing? So this thing is estimated in a similar fashion. Now, this is an L2, and for this one, we have a bound on the infinity norm. So, so this is the 2 norm of V1 times the infinity norm of u. Now we can use this functional analytic estimate that we proved last time. So this is small equal than C V1 2 norm lambda minus 1/2. So the norm of the Laplacian plus C lambda 3/2 V1 2 norm the norm of u. Right, so that's because of that estimate. So all in all, we get the following. So let me denote this guy by alpha. And now let's choose. Let's choose lambda such that this expression is smaller than 1.
When there's a square?
No square, yeah, good. Why is it only Jan Peng who notices those mistakes? Right. Okay, so here is our final estimate. Now the norm of the sum is bounded by the sum of norms, and the estimate gives alpha times minus delta u, the 2 norm. So plus, there will be all this garbage, right? So this guy plus that guy. So here we don't have any control over the coefficients, but it doesn't matter. Let's denote the sum of those 2 coefficients by beta. So there is this guy. So that's a Carter-Ehrlich estimate, which now makes Carter-Ehrlich work. And technically speaking, it shows that A is essentially self-adjoint on nice functions, right? We chose some space of nice functions, and then those nice functions, they are dense in the domain of Laplacian. So by Carter-Ehrlich, A is self-adjoint on the domain of Laplacian. Okay. Yeah, sorry again. So last time it was not really complete. There were still some steps left. But maybe if I make mistakes, which I do often, you should tell me. Now let's use, so let me give one example of using this theorem and also some other facts about self-adjointness or not self-adjointness of operators of that type. So one remark is that the theorem implies the following. So let's take A to be minus Laplacian minus some positive coefficient divided by R, where R is the distance from the origin. So that's of course a very, very important physics example because this potential is a Coulomb potential. Now notice that this operator by itself, the multiplication by this thing, is absolutely unbounded from below, right? Because it's negative. So and it is not obvious at all. It is defined on the domain of definition of minus delta. Why should it? But now this theorem says the following. You see, let's do the following thing. Let's introduce a function chi of R, so on the positive semi-axis. So let's take 1, and let's first go as a constant equal to 1, and then smoothly go to 0. Right? Let's take such a chi function, and let's say that v1 will be chi of R times v of x. So v of x is this expression, and then v2 will be 1 minus chi of R times v of x. Well, now this guy is bounded, right? Because we take away, 1 minus chi vanishes near the origin. So we take away the region where this guy has a divergence. So this guy is bounded. What about this guy, right? So we cut off long distances, and near the origin 1 over r is square integrable on R3, right? Because it's square is 1 over r square. In the volume integral, you have r squared dr. So this guy is square integrable. So this means that this operator is self-adjoint. And bounded from below. Now, let me ask experts in quantum mechanics. For this particular operator, do you see some other way to prove it without using the huge machinery, or with using some other huge machinery? So how to see that this thing is self-adjoint and bounded from below? Right? So that's a Hamiltonian of the hydrogen atom. So you people who already had physics, quantum mechanics, so how do you prove that it's self-adjoint and bounded from below?
We solved equations for eigenvalues and eigenvectors.
Yeah, that's right. So the other way to see it, remember, if you know, if you have a Hilbert basis, of eigenvectors and we know eigenvalues, right? So then for this thing we can explicitly solve for a Hilbert basis of eigenvectors and eigenvalues, and this already implies that it's self-adjoint on some appropriate domain and bounded from below. We just check that those eigenvalues are bounded from below. So that would be an alternative way to do it. Of course, as I say, maybe one can say it's an elementary proof. Of course, one still needs some kind of Fourier analysis to see that this is we do get a Hilbert basis, but that would be another way to see it. Of course, this theorem gives you more. You can modify this potential, whatever, to make it not exactly solvable. You can still see that this is essentially self-adjoint. So note that our proof worked in R3. So one of the exercises for later today to see that it works in R, it also works in R2. But maybe when you look at the exercise, it's good also to check it actually doesn't work starting from R4. So then the argument breaks for some reason. So now for any n, the following facts are true. So we consider this operator and we assume that v of x is bounded from below. And of course real. I always assume that v is real. Then A is always self-adjoint or essentially self-adjoint depending on the domain you choose. For example, in dimension 1, maybe let me call it A. So if you add the square potential, so that's also a very important example known as the harmonic oscillator. Perhaps we'll come back to it later in the course. So this would be an example, right? This is clearly bounded from below, so this is self-adjoint. Now another funny example, let's assume that v of x is bounded from below by minus q of r. R is the distance. And q of r is a monotonously increasing function, something like this. And there is a condition on q of r. We assume that the integral, let me assume, to simplify things, that q of 0 is strictly positive. And let's assume that this integral, dr over square root of q of r, diverges. Later on in the course, we'll see reasons why actually this integral. At the moment, it looks mysterious and quite arbitrary. But later on, we'll see a little bit why. So then, if this is true, then A is self-adjoint. A couple of concrete examples, which are important examples. So again, for g equal 1, the linear potential. So this is self-adjoint. So we can choose Q of R equal to AR, let's say AR plus 1, say, to avoid difficulties at 0. And of course, so this integral diverges, so therefore we are good. Say another example. Now you take this kind of inverted harmonic oscillator. So say Q of R is equal to, say, R squared plus 1 times A. And of course, again, the integral diverges now logarithmically at infinity, so that's still true. Now an interesting counterexample. Let me finish with an interesting counterexample. So let's increase the degree. So I have this inverted potential, but now it falls as x to the fourth. So we don't satisfy this condition, so we cannot conclude it's self-adjoint. But actually, it is not essentially self-adjoint. And later in the course, we'll see some reasons why. But you know, it's interesting. You don't get this example in physics applications. And okay, difficult to say what's the reason. Kind of depends what the God developed first, the quantum theory or the theory of unbounded self-adjoint operators, right? That depends on the reasoning, right? We can say if the theory of unbounded operators was developed first, that's why, of course, right? Once you figure out it's not self-adjoint, you don't put it in the universe, because then the universe will not function, right? or of course, the physics reasoning is different, right? The universe, as we know, was created at some point, and then since it functions, it cannot have those examples because, right? So I don't quite know what's the correct order of things here. Okay. So. Right, so much I wanted to tell you to wrap up the last class. Now, today, the big topic that we're going to discuss is the spectral theorem. So I must say, up to now, in this function analysis part, we were trying to more or less properly prove things. But today, we're not going to prove things at all. So instead, I will formulate the theorem, and I will try to give you a couple of examples to more or less explain how it works. So that's the strategy. Because that would be really a big chunk. Maybe for us it's not justified to dive into it. So the topic is spectral theorem, and I will start with one definition. Right. So let's say A d of A to H, an operator possibly unbounded. And we say that the resolvent set of A is the subset of the complex plane such that the operator A minus Z, as usual we assume that Z is multiplied by the identity, is invertible. So then the spectrum of A is the complement of the resolvent set. So these are all the Z's for which A minus Z is not invertible. Now, effect, we won't need it so much, but still, probably for you, it's good to know it. So the resolvent set is an open subset of C, and the spectrum, usually denoted by sigma of A, or that's one possible notation. And then, of course, sigma of A is closed. Now, if A is self-adjoint, then we know that A minus Z is invertible for all Z outside the real line. So remember, we proved it for the imaginary axis outside outside 0, but of course by real shifts don't matter. You can always modify the arguments we gave before, and we'll see that A minus Z is invertible on all of the open upper half plane and all of the open lower half plane. So this means that the spectrum is contained in R. Now let's look at a couple of examples, and this will be our guides and examples for today. So the first example, let's recall that at some point we looked at the momentum operator minus I d over dx defined on d of A, which were continuously differentiable functions on the circle. So it's essentially self-adjoint, and we actually know the explicit set, the Hilbert basis of eigenfunctions, right? So if we choose En of x to be 1 over square root of 2 pi exponential I in x, this is the Hilbert basis, and we know that A En is equal to n En, right? So we know eigenvectors and eigenvalues of this thing. So let me make a drawing. And we'll do the construction which we'll later generalize. So let's say that's our complex plane. That's the real line. And on the real line, let's mark integer points, right? So let's look at the operator a minus z. Well, we still have the same Hilbert basis, which is a basis of eigenvectors for a minus z as well, right? So this is n minus z times en. Now we can try to define the inverse operator. Let's just simply try to define it by this formula. So the question is whether it works. And obviously it does work for all z outside the set of integers. Real or non-real, doesn't matter. I can, for instance, put my z here. If I choose a z outside the set of integers, I see that the absolute value of n minus z inverse is bounded. So this does define a bounded operator. And moreover, if z is real, this bounded operator will be even self-adjoint. Right? So, so this means that sigma of a is contained in z. And it's actually equal to z, because if you're sitting at this point, if you're sitting at an eigenvalue, then a minus z cannot be invertible there, because you're just killing one of the eigenvectors, right? So you can, whatever, no way you can go back. So in fact, sigma of a is equal to z. Now, another example that we're going to look at. We choose H to be L2 of R, and the operator will be multiplication by x. So the domain, let me recall, I think this was one of the exercises. So these are L2 functions such that this integral converges. Right. Well, now again, we can try to define the inverse. So a minus z acting upon u is simply equal to x minus z times u of x. Again, for all z's outside the real line, the inverse of this guy is clearly bounded. So we can easily define a bounded operator, which is simply multiplication by the inverse of this function, bounded for z outside the real line. However, clearly it doesn't work on the real line. So you can always you can always find functions for which this will not be in L2. So this does not define an operator on the whole of L2. And so in this case, sigma of a is simply equal to the real line. So that these are two important examples that we're going to be looking at. So now, before the break, let me still recall one thing from the finite dimensional theory. So remember, we had some kind of strange definitions of those projection valued measures, right? And they looked really too complicated for linear algebra. But now they will be very useful. So let me recall. So a projection valued measure. So this is an assignment to each measurable subset of R. One associates an operator. To E, we associate an operator P of E. And this operator is an orthogonal projection. Maybe I should say bounded. So these are bounded operators. So P of E squared is equal to P of E. So they are self-adjoint. P of E star is equal to P of E. And just by definition, P of the empty set is a zero operator. P of the whole real line should be the identity operator. And suppose you have an infinite family. So the elements of this infinite family are disjoint, and we denote by E the union, the infinite union of those sets. So then we say that P of E is the sum, infinite sum, or infinite series, sum of the infinite series of PE of n's. Or let me write it in a slightly more detailed way. Limit and now here, actually what I wrote here is wrong, or it's unreasonable. So let me correct it. So actually one should do it in this way. Let me add in a different color. So for every vector in H, so this vector is a limit of those vectors. What's the difference between what I wrote before and what I wrote now? What I wrote before, implicitly, it was saying that this sequence of operators converges to that operator. But like basically, when you're saying it, you assume this is under the operator norm, right? I mean, that's how you usually think about it. And here what I'm saying is that for every vector, the images converge to the image. That's not quite the same thing. So this property here, it's called strong convergence. And strong, this means that we do it on every vector. Strong is a somewhat misleading word because strong convergence is much less restrictive. It's much weaker than the operator convergence. Operator convergence implies the strong convergence, but why I'm saying that the operator convergence is unrealistic? What's the norm of a projection? So suppose you have a projection, self-adjoint projection operator. What is its norm? Its norm is equal to 1, right? Now, suppose I'm looking at this guy, at this sequence, and I want to see whether it is at least a Cauchy sequence of operators. What would be the difference of two terms for big N and for big M? This would be some sum of projections. Actually, this will be a projection on something. So its norm, like for n different from m, will always be equal to 1. Whatever you do, right? You can take n million or billion, whatever you want, right? Then still, it will not satisfy the conditions on the Cauchy sequence. The norms of differences, they are always equal to 1. Nothing happens to them. So therefore, those just to warn you, those sequences typically never converge as operators, but they converge in the different topology. So that's also called the strong topology, and this is this one can postulate. So basically, if you postulate operator convergence, there will be 0 examples, roughly. Okay. Maybe just one more notation and one remark. So a piece of notation. We denote by P of lambda P of the open semi-axis from -infinity to lambda, not including lambda. So this is a particular subset of the real line. So we call this guy P of lambda. And then here is the following fact. Suppose we choose some U in H. So then we can consider a function of lambda. So just a Hermitian product of U times P of lambda times U. Maybe let me recall that at some point, right, we already saw it in the finite dimensional case, and these are some kind of probabilities of measurements, right, for pure states. Now let's take the differential of that function in the following sense, right? So you have a function which is increasing and which is bounded. And you may or may not remember from functional analysis that derivatives of such functions can be interpreted as measures. Is a measure on the real line. So we'll be using those measures in the formulation of the theorem. So actually, from each projection valued measure, you can build many measures on the real line, and that's what we've already been doing in the finite dimensional theory. So I suggest we make a break. And would it be okay for you to have today a short break? Because again, with those schedules, right, Yan Peng and I, we have to run to some other event after the talk. So maybe we make a 5 minutes break. Would it be okay? Okay, thanks. All right, so let's continue. So now spectral theorem. It will come in two parts. So part one. So let's assume that we have a self-adjoint operator. So then there is a unique projection valued measure on R. Let's call it PA. Such that the following things are true. So first of all, there is a characterization of the domain of A in terms of this projection valued measure. So these are all the vectors in H which satisfy the following property. So the integral of lambda square with respect to the measure that we just introduced, right? So we have just a normal measure on the real line. So that's this one, which is associated to the vector. And the integral with respect to that measure of lambda square should be finite. Now, so then there is also the following formula for the action of the operator on a vector from the domain. And so let me write it, and then we'll discuss it a little bit more in a minute. So you see here, this was P of lambda. Those were projection valued measures. We can act on them by those operators on vectors. We obtain in this way some kind of vector valued measure. So we integrate with respect to this vector valued measure just the linear function lambda. And this gives us the operator. So that we'll discuss a little bit more in a second. And maybe let me write for completeness one more formula. So the quadratic form of A is equal to the integral over R, again of a linear function, and now with respect to the normal measure. Right. So basically, there is a trade between those operator valued measures and the self-adjoint operators. We saw that in the finite dimensional case, those statements are basically statements of the ordinary spectral theorem. And this is a formulation which generalizes to the infinite dimensional case and even to the unbounded case. Now, let me look at the examples, and let me look a little bit, just try to explain what some of those formulas mean, especially this formula. Right. So our first example, right, what an operator A, so maybe I should say examples. So we had that operator A with a Hilbert basis, En, and eigenvalues n. So what's the projection valued measure? First of all, for each of the basis vectors, we can introduce a projection on the one-dimensional subspace. Let's call it Pn. So this is given by the formula we've already seen in the finite dimensional case. Simply you project to the basis vector and you multiply by the basis vector, right? So these are one-dimensional projections. And then here this will be sum over n in E intersection with z of Pn's. And again, we say that this is right here. If E intersection with z is infinite, there is some kind of limit procedure inside. So this limit is with respect to the strong topology. Maybe let me write it, let me indicate it. So that's a strong topology sum, because otherwise maybe it simply does not converge under the operator norm, but it would always strongly converge. Right. Now what are those functions? Say, suppose I choose u in H, and I consider this function of lambda. So let me write it in the following way. This is sum over m, um, em. Here this is the p of lambda, sum over n, un, en. So those sums, of course, converge in the norm of H. Now p of lambda acts, maybe I should write it as well. P of lambda is a sum of n smaller than lambda, Pn, right? So so it will act by 1 on all n's smaller than lambda, and by 0 on all n's bigger than lambda. So that's this. And so this is equal to the sum n smaller than lambda un squared, right? So these are those functions. Well, so if I try to draw a graph of such a function, so what happens, it's similar to the finite dimensional story. A priori, each integer, it may jump. It may not jump, depends, right? Depends what is un squared, right? But a priori, when you're passing an integer, you are adding. Yeah, you're adding. I think how is it? No, I think it's like this, right? Sorry, yeah. Maybe that you shouldn't trust me. You should check. So which value is excluded, and then. So it goes from 0 at minus infinity somewhere to 1 at plus infinity. So this is a function which increases in steps. So the derivative of this function is a measure on the real line. It's an atomic measure with support at integers. And this is simply sum over n un squared. And those atomic measures we denote by delta lambda minus n d lambda, but this stands for the atomic measure. So maybe just to check what the theorem was saying, right? So suppose I want to compute the quadratic form. So the theorem is saying that I should compute this integral. Well, what is this integral? So I'm integrating this linear function against the sum of atomic measures. And of course, each atomic measure, it simply evaluates this function at lambda equal to n. This is by definition of the atomic measure. And that's the expression that you expect, right? That's the expression that we already know to be true. Just to tell you how the spectral theorem in this case reproduces the result that we already know. Now let's look So now let's look at this second example. So this was h equal to L2 of R and x and a equal to x. So in this case, what is this projection valued measure? So let me simply write a formula for it, and that's a formula that we already seen in the exercises long ago, right? So we act by this gadget on some element of L2, and we want to know what is it as a function of L2. So here, let's simply take the characteristic function of E. So that's the function which is equal to 1 if x is in E and 0 otherwise, and simply multiply U by this thing. So we already seen that example. I don't know whether you remember in one of the exercises. In particular, PA of lambda will be a step function right? So the step function of x is 1 if x is greater than 0 and 0 if x is small or equal to 0. Say at 0 doesn't matter so much. So basically what those projections do, suppose here is your L2 function, and I choose some particular lambda. So then the result of the action of the projection will be as follows. So it will be 0 for x bigger than lambda. And here I simply copy the graph. Clearly it defines here a bounded operator. One should check that this is indeed a self-adjoint projection. Okay, very good. Now, now let's see. Maybe what I want to do is the following. Let's just check that the domain of definition is correct. And after that, I would like to discuss a little bit this tricky formula which was in the middle. So let's say the claim is that the domain of A, or maybe for that let's first compute this this function. So u pa lambda u, right? So this will be an integral over r u bar of x times p of lambda u of x dx, right? And since there is this theta function here, so this is simply an integral of minus infinity to lambda u of x squared dx. So that's how this function now looks like. So recall that before those functions, they would be step functions, right? They would jump at the points of the spectrum. Now the spectrum is all of R, so this will be more like a nice function, right? So this is a square integrable function. This is a clearly monotonously increasing function of lambda. It starts from 0 at minus infinity. It's bounded by 1, and it goes to 1 at plus infinity if u were normalized, but if not, it goes to the norm of u squared at infinity. Right. So now d of this guy is simply u of lambda squared d lambda. So that's the density of our measure with respect to the Lebesgue measure. So it's a square of an L2 function, so it's an L1 function, which is positive and defines for us a measure. So now the domain of A is supposed to be vectors in H, such that the integral of lambda squared with respect to that measure be finite, right? And look, with kind of if you exchange lambda by x, this will be the original definition of the domain, right? So that's the right domain. So the theorem obediently reproduces the results that we knew before. So now maybe a small remark. So I wrote this formula. So what does it actually mean? Now, so you see this integral is some kind of a Riemann type integral. Now, what's the Riemann integral over R? So there are two things about when you construct just for normal functions a Riemann integral. First of all, it's an improper integral. So this means that you should construct it as a limit for some R going to infinity of some kind of integrals of that type, right? Now, what are those integrals? So those integrals, when you construct Riemann integrals, typically, right? So there will be one more limiting procedure, some delta going to 0, and here you would write Riemann sums. Right, so we'll write Riemann sums of what? Kind of here with the measure, you would put let me do it this way, for instance. So let's split our interval from minus r to r into some small intervals, right? Here we write a measure, a projection valued measure corresponding to that segment. So I make them all disjoint, and I act on my vector. So I get vectors. And here I should write whatever I like, right? A half sum or lambda I plus 1. Let's say some mu I. Mu I is in this segment, and delta is a max of the lengths. Right, so this integral is defined as a Riemann integral. Essentially, you copy the definition of the Riemann integral for the finite segments, and then improper Riemann integral you kind of. And of course, the claim is that this whole thing now should converge. Converge where? In H, right? So this is just for you not to have it as an abstract symbol, but yeah, the construction behind it would be a Riemann integral. Note that we don't need a Lebesgue integral because we are integrating nice functions. For instance, here it's a linear function, right? So the Riemann construction is quite sufficient for that. Now I would like to continue with the statement of the theorem. Recall that I now showed you part 1 of the theorem. Let's now do part 2. Yeah, it's also known as a functional calculus. Now, again, we have, as before, the self-adjoint operator. Now, PA is the corresponding projection valued measure. Now suppose we take a function which is a continuous function on R and, well, possibly complex valued. So then we'll define an operator denoted by f of a. And to define an operator, we need to say what is the domain, and we need to say how it acts. So the domain will be as follows. Now you can actually easily guess it. So I'm just replacing lambda by f of lambda in the definition of the domain that we had before. And for a vector in such a domain, We just copy the formula. So this operator is well defined. That is, this expression does converge to something in H. So this condition guarantees this fact. And then the following properties hold true. So the adjoint of this operator is equal to the function f bar of A, where this is just a complex conjugation of the function. Right? So this was a function of a real variable with possibly complex values, so we just conjugate that function, we obtain a new function, and that's the adjoint of that operator. So in particular, this implies that if f is a real valued function, then the corresponding operator that you obtain using this functional calculus is self-adjoint. So you can take any exotic function you want, it gives you a self-adjoint operator. Now the second property, suppose that f is bounded on the spectrum of A. It doesn't need to be bounded on the whole of R, but if it's bounded on the spectrum of A, then Fa is a bounded operator. And finally, suppose that f and g are bounded on sigma of A, so two functions which are bounded on sigma of A. So then the product of bounded operators, f and g, is the bounded operator which corresponds to the product of functions. So all in all, it's a pretty powerful machinery. So let me give you a key example of the use of the functional calculus. So here is an important example. So for S in R, consider a function which is the exponential of is lambda. So for every self-adjoint operator, this gives a definition of the whole family of self-adjoint operators. So there is a maybe special notation. Let me call it US of A. And this is simply the exponential of ISA in the sense of the functional calculus. It is, so the following properties are more or less obvious. So if we put s equal to 0, right? So then u0 of a is an integral over r of the function 1. Of our vector valued measure. And this is the same as p of infinity u. That is p of the whole real line acting on u. And that's the identity operator, right? So for all operators a, u0 of a is simply identity. Now f is bounded on R. So which means it's bounded on all the spectra which are contained in R. So it's bounded for all S. Now yet another property, obviously exponential is lambda times exponential it lambda is exponential is plus t lambda, right? Which means that us of a times ut of a is u s plus ta. So the complex conjugate of this function is equal to minus is lambda. So this means u star us of a star is equal to u minus s of a. And of course, this implies us of a star times us of a is u minus s of a us of a. And by this property, it is equal to u0 of a, and it is equal to 1. So all in all, if we summarize, us of a is a one-parameter subgroup of unitary operators on H, right? So this condition says that it's unitary, and this condition says it's a one-parameter subgroup. So this those statements, this example is hugely important. And that's for the following reason, right? Suppose that H is the Hamiltonian of our quantum system. And We always assume that the Hamiltonian is self-adjoint. So there is always a lot of physics and mathematics discussions on the self-adjointness of the Hamiltonian. And one of the main reasons for that is that if H is self-adjoint, then we can define the evolution, the unitary evolution apparatus. So here, of course, we have this funny notation for the for the S parameter. S is minus T over H bar, but doesn't matter, right? So this is a one parameter group of unitary evolution apparatus. So that's in particular why we are not happy of having symmetric Hamiltonians. So we want self-adjoint Hamiltonians, because if you want to define Hamiltonian dynamics, you have to be able to write this formula. And as you see, writing this formula, what does it mean? Now, if an operator H is infinite, is on the infinite dimensional space, it's possibly unbounded, it's not kind of, we cannot envisage just taking the power series definition, right? So it doesn't make any sense, usually. However, this thing, according to the functional calculus, it does make sense. So we're going to see examples of it. But now maybe let me finish with two simple examples of one parameter of those exponential subgroups. So, so simple examples. So let me start this time with the example 2, right? Example 2, I recall A was x hat. Well, in this case, US of A, x in con U. Here you can easily guess what it is. So I computed at the point x. Well, yeah, you just multiply your function by this unitary factor. And that's what the definition will give you. Now, somewhat more interestingly, for the first example, so you will have an exercise to that effect in the next problem set. But now, kind of probably our quantum mechanics experts can simply tell us how this operator going to act. So we consider this operator x in con U. U is a function on the unit circle, right? So it's a function of periodic function of x with period 2 pi. Now, so quantum mechanics experts, what is it?
U from x plus s.
Yeah, this must be, this better be Q of x plus s. So this will be one of the exercises of the problem set 8 to establish that formula. Right, as you see, at least in those simple examples, those one parameter subgroups are really nice operators on L2. They look quite manageable. Of course, for typical Hamiltonians, maybe it's less manageable, but still, to some extent, a big part of the rest of the course, you can say, will be devoted to the questions of what we can say about spectra of Hamiltonians and what we can say about the behavior of those evolution operators. So in fact, so the functional analysis part now ends here. Of course, one could have given like maybe several semester-long courses on the functional analysis of quantum mechanics. But what we'll do after the test, in 2 weeks from now, we'll start looking at the problem as a differential equations problem. So typically, operators in quantum mechanics, they are defined as differential operators, as we saw it. And, well, solving differential equations, that's a different, in some way, different part of math. So we're going to look at what differential equations theory has to say about it. Okay, well, that's it for today.